Hey guys, this is GKCS. This is the very first lecture on competitive programming in Java, and it's based on good coding practices. So, the first thing we want to know is how can good coding practices help us? The answer to that is it can help reduce our time investment and also effort investment. So basically, we'll be able to solve more problems in lesser time and also be fresh relatively for the next problems which are coming up. So for a given program, how do we define how good it is in terms of a coding contest? And three indicators are very useful when looking at a program. The first one is correctness. If the program is not correct, it doesn't matter how efficient it is or how good it looks, it just doesn't work. So that's the very first thing that we should look at in a program. uh, Second one is efficiency in competitive programming. If a program is not efficient, it's not going to make the mark, and again the other parameters fall out. And the final thing that we look at is debuggable. So usually people don't focus too much on debugging programs or making them debuggable, but um, in case our program is not correct, then the most important thing immediately becomes making it debuggable. So let's discuss on how are we actually going to get these properties into our program. So as we discussed, the very first one is correctness. Uh, Making a program correct is actually quite simple but not easy. Um, Once we have thought of an algorithm which is reasonably efficient, we can tell that looking at the constraints, that okay, it's n log n or n square or on, whatever be the case, we have to always write test cases to be sure that a program works. If the program is extremely simple, maybe we can skip writing test cases altogether and just submit the solution. But I would suggest for any program which is a little complicated, or even programs which have scope for going wrong, writing test cases is always safer than getting a penalty for a wrong submission. Uh, so let's see how we can do this. The first thing is we want to make our program testable. So we take whatever logic is in the program and we make a new class called solver. You can call this class anything as long as it has a function which returns your result and takes in your input parameters. So here we can see that the input parameters required for uh, this solution is n, m, and some variable k. So these are usually these are input in the coding contest problem, and a is something that we read in again through input. So a is an array. I think it's a boolean array. And string builder was actually taking the result and returning it. What we'll be doing is returning a string. So yeah, and now we can return the result. So you see, what we have done is take a big fat main program and convert that into something smaller. We have separated out the logic from the main function, and this is often very useful because uh, it provides separation between logic and other tasks. Those other tasks might be taking in input, output. They might be doing some pre-processing, but usually you want to separate out your logic from any other task in the program. So here, of course, we need to create a new solver object and solve it for this particular n, m, k, and a. Now let's see how do we test this program. So Java has this interesting framework called JUnit, and if you use this, you will see that it has some annotation syntax and all that. But the most interesting thing is there are methods like assert equals, assert true, which you can go through, but they're pretty easy to understand. What happens is they take a parameter of expected, which is the expected result. Here I'll be just putting a random expected result, and the second parameter is called actual. So this is what we get as a solution from our solver, and this is usually manually entered as the expected value for any given input. Let's give an input of just some random input here. So later on you'll be seeing how we can automate generating expectations in um, um, testing through multiple solvers. But for now, we need to enter this expected value manually, and um, the actual value will be through the parameters we'll be passing to our solver function. And this pattern is very often visible in programming competitions. Through many programmers actually use this pattern of uh, creating an object and calling it solve method with a set of parameters to get the solution. The next thing we need to look for when it comes to correctness of a program is checking for overflows. Usually we can avoid this by using data types like long or double instead of float or int, but even then there might be cases where you'll have some integer overflow, or in case you're doing some division operations, just make sure that um, integer division does have certain truncation with it. So it takes hardly a minute to just check for any overflow possibility in the program, and also just looking at the constraints usually is enough to tell us whether there's any scope for data type overflow. So now that we have looked at the correctness of a program, the next thing we want to see is whether a program is efficient enough. So obviously the basic thing to do here is to check whether our algorithm is correct and fast enough for the given constraints. Usually we can assume that if there are 10 raised to the power 8 operations to be done, those operations can be done in 1 second. So if n is 10 raised to the power 7, it's safe to assume that our algorithm needs to be on. On the other hand, if n is something like 10 raised to the power 6, then our algorithm can survive a n log n complexity also. Usually n square, using the same logic, can survive a on square algorithm. N square being 10 is to the power 8, which means n is 10 is to the power 4. So once we have decided what kind of algorithm we are going to use, there are still ways to optimize the program. Now, as they say, premature optimization is a sin, but if you are seeing that your algorithm is theoretically fast enough, but for some strange reason technically is not making it, there are a few ways in which you can optimize this scenario. The first thing is using the correct access modifiers. There's no reason for making all our functions public or static or something as weird as that. Usually we just want our main function to be public static, and the solver function's primary function, which takes in the input, as being public. The next thing to do is see which variables do not need to change and marking them up as final. For example, string builder here, we are not going to be changing the reference of string builder in this program, so just marking it as final is a good practice. Similarly, sums. The next thing to look at is making sure that your input and output operations are fast enough. Uh, Simply not using scanner is usually enough for making your input and output operations quite fast. But if you're doing a lot of input and output operations, using a fast input reader and aggregating all your output operations into a single output operation as shown here can really speed things up. We'll discuss this more thoroughly in the third lecture of fast input output, so don't worry if you didn't really understand what I just said, but just remember that the third thing, maybe if your program is very slow, is just have a look at the input and output operations you're doing. If it's the standard thing that you do all the time, no need to even think about it. But otherwise, if you're using something like a buffered reader, or definitely scanner is too slow, but buffered reader also, just have a quick look at your IO operations. Next thing to look at when you're making your program efficient is trying to avoid object creation. So, and even if you are, they shouldn't be of the order of n square or n log n. Certain cases are okay. I mean, you can use really small objects to represent your data types, but otherwise creating objects is always quite expensive, and in a competitive programming problem, usually you can substitute your objects for simple integers or long. So if there is, let's say, a binary trie that you need to make, and every node in that trie has a left and right pointer, we need to start considering whether this data structure is going to be efficient enough. And the best thing to do is actually use arrays in such a way that you can just avoid this object creation as much as possible. Finally, when it comes to efficiency, what we want to see is avoiding initializing arrays many times, especially if they're large arrays. For example, quite a few competitions have this number of test cases given to us. Sorry, reader. And what happens in every test case is we need to print something. So when we initialize an array, let's say every time in this test case, and this array size is pretty large, it becomes quite an expensive operation to create this array every time for each test case. So if this array is going to be overwritten and we already know the size of the array that we'll be using, it's simpler to initialize it right here with the maximum constraint value n here. Let's say it's 1,000,000 for now, and whenever n will be input, we'll know up to what point of the array that we need to read. So, and also marking it final is not a bad idea. And this too. Yeah. So these are ways that in which you can make your program more optimized, but Again, I would suggest that only if your program is going above the time limit is the time when you start looking for optimizations. Otherwise, the best algorithm is usually more than enough to get your problem through. And so it's now time to discuss the final parameter that we look at in a good program. It's how debuggable it is. The simplest way to make your program debuggable is separating your logic with your IO operations. We have already done that, and so the next thing we'll be looking at is what a function should do. If you have a look at this function, although the logic has been separated, it's still pretty complicated. Looking at this, I can't tell what it's doing. So there's totals and sums here, so it's not making much sense to me. Because I've written this program pretty recently, I know what sums means. This was a dynamic programming problem, and sums actually is the number of ways through which I can go through this maze. So I'm going to rename the sums variable to ways, and the boolean array a is nothing but the maze itself. Simply doing this can really help us figure out where do we need to change our code, whether we can extract out certain parts of the code into functions, and that's the reason why I would also suggest that the variable naming should be quite good. It really helps in converting your program into a debuggable program. Now, as we see, this part of the program is just taking all the number of ways and then summing them up. Typically, we don't want to be doing this in a in the same function as the one which is populating the number of ways. So I'm going to take this and get it into a different function of some number of ways, and that's it. Now, some number of ways can be tested separately. If we are very sure about its logic, it never needs to be seen again, and this thing can really help reduce the headache we have on this big function called solve. Also, essentially what's happening is we are getting the string builder from this point. So I'm going to be putting the string builder here and converting this into a function called getResult. Again, getResult is pretty simple to understand, and because it's so small, it's very easy to just read through the code and tell whether it's going to go wrong or not. So getResult becomes simple. Sums becomes quite simple. In fact, we can just directly pass these variables in. So you can see from a pretty complicated program, we have made it much simpler just by delegating the tasks that this single function had to smaller and simpler functions. Finally, I would like to discuss three small things to make your program far more debuggable. One is not using too many global variables. Private, final, who knows what, int x equal to 10,000. And then what ends up happening if this variable is not final is somebody's setting x here, and somebody's setting x maybe here too. So it becomes confusing where and who is setting x. I would suggest you avoid these global variables as much as possible. They not only make the function complicated, but it's also very difficult then to extract out the logic into a different function. The second thing is using as many library functions as possible, because they not only are heavily tested by Java developers, but also using them is usually simpler than writing our own functions down. So for example, there's binary search, and this has already been implemented for various cases. So you pass in an array, you pass in the key, and that's it. You have binary search already for you in a library function. Similarly, sorting, if you want to make this parallel, you can make it parallel sort. And using these library functions, you can actually read how efficient they are, or how what kind of parameters are they expecting, what are the possible side effects. But usually these library functions are very intuitive and do absolutely nothing different from what they say they will. Parallel sort will just sort it parallelly through a parallel algorithm. So using as many inbuilt functions as possible is almost always a good idea. There are certain weird cases like strings index of operation, which is not efficient enough for most programming computations. This is an on square operation, but otherwise, usually the inbuilt functions are not only easy to implement but also very efficient. And the final thing I'd like to say is, when you're writing a program, make it as easy it is for you to understand, because running through the function names, trying to understand what the variables were doing, even if it's a short competition, it's happened to me that I just forgot what this variable is doing, and then I have to run through the code just that one extra time to figure out what's happening. And although it might seem like one extra time is not a big time investment, actually naming that variable sensibly would have taken lesser than that. Similarly, when you're testing the program continuously, writing these tests down is a time investment for once, but losing that 20 minutes in the programming competition, or even just locally going on running the same test through a input and output operation, is much slower usually than just writing the tests down. So that's it on this first lecture of good coding practices in competitive programming. Um, I know that it's been a really long lecture and quite a few things have been said in this, but if you go back and try and actually implement these practices, I assure you within a few weeks you'll start seeing differences in not only the time and effort that you invest, but also maybe the satisfaction that you get when you actually solve a problem. So if there's anything that you have not completely understood, or something that you just disagree with, leave it in the comment section. I'll try and respond to every comment. Also, quite a few of these things that I've discussed today are not only through reading books on good programming principles, but also through experience. So if there's something that doesn't work for you, then let's discuss it. There might be some coding practice that you don't find very suitable. So well, that's perfectly fine. You Whatever works for you is usually quite good, but these principles have been used extensively. So at least what I would say is that you can try it out once. And in the next lecture, we'll be talking on test case generation. So I'll be seeing you there.